You're watching this video right now because billions of light pulses just traveled thousands of miles through cables buried under oceans, mountains, and city streets to reach your device. But here's the thing. Most people have zero clue how any of this actually works. And honestly, that's kind of wild when you think about how much we depend on it. So let's fix that. In the next 10 minutes, I'm going to show you exactly how the internet works, from the moment you hit play to the pixels dancing on your screen right now. No boring jargon, no AI generated nonsense, just the real deal explained so clearly that your little cousin could understand it. Let's dive in. The journey begins. Right now, this video lives on a Google server somewhere, probably in a massive data center that's the size of multiple football fields. That server is basically just a really powerful computer with a solid state drive, storing this video as a huge collection of zeros and ones. Your job? Get those zeros and ones from that server to your phone or laptop, which could be literally thousands of miles away. Now, you might be thinking, why not just use satellites? Good question. Satellites seem perfect, right? They're floating up in space, they can beam signals anywhere. But here's the problem. Most communication satellites sit about 22,000 miles above Earth, so your data would have to travel 22,000 miles up, then 22,000 miles back down. That's 44,000 miles total, and even though these signals move at the speed of light, that distance creates a noticeable delay called latency. And latency is the enemy of everything we do online, from gaming to video calls to just loading a simple web page. So satellites are out. Instead, the internet relies on something way cooler, a massive underground and underwater network of fiber optic cables that literally connects the entire planet. The secret network, under your feet. Right now, there are about 1.5 million kilometers of fiber optic cables, crisscrossing the ocean floor. That's enough to wrap around Earth almost 40 times. These cables aren't thick either. Most are about the width of a garden hose. But don't let that fool you. A single modern cable can transmit 400 gigabytes per second. That's insane. How do they lay these cables? Specialized ships drag massive spools across the ocean, literally unrolling cable at about 10 kilometers per hour. When they hit bad weather, they sometimes have to cut the cable, tie it to a buoy, and come back later when the storm passes. And here's the wild part. Sharks occasionally bite these cables. This actually happens. Google's had to armor their cables because sharks kept chomping on them. But underwater cables are just one piece of the puzzle. Eventually, these cables reach land, connect to more cables, wind through cities, and finally reach a cell tower or a router in your house. Whether you're using Wi-Fi or cellular data, at some point your connection plugs into this physical network of cables. How does your device find the right server? Okay, so we've got cables connecting everything, but the internet isn't just one big pipe. It's billions of devices all trying to talk to each other at the same time. How does your phone know where to find this specific video on a specific server thousands of miles away? This is where IP addresses come in. Think of an IP address like a home address, but for devices. Every single device connected to the internet, your phone, your laptop, Google servers, everything, has a unique string of numbers that identifies it. It looks something like 172.217.14.206. When you want to access something online, you need to know the IP address of the device that has it. But here's the thing. Nobody wants to remember a bunch of random numbers. Imagine having to type 172.217.14.206 every time you wanted to watch YouTube. That would be awful. So instead, we use domain names like youtube.com or netflix.com. These are way easier to remember, but your device still needs the actual IP address. So how does it get it? Enter the DNS, or domain name system. Think of DNS as the internet's phone book. You give it a name, say youtube.com, and it looks up the corresponding IP address and hands it back to you. Here's how it works in practice. You type youtube.com into your browser. Your browser sends a request to a DNS server, usually run by your internet service provider, saying, hey, what's the IP address for youtube.com? The DNS server looks it up and responds with the actual IP address. Your browser then uses that IP address to connect directly to YouTube's server. And boom, the video starts loading. The magic of data packets. Now, here's where things get really interesting. When Google's server sends you this video, it doesn't just shoot the whole thing at you in one massive chunk. That would be wildly inefficient. Instead, it breaks the video down into tiny pieces called packets. Each packet is like a little envelope Inside, there's a small chunk of the actual video data, just a few thousand bits of those zeros and ones, but the packet also includes some crucial information on the outside, the IP address of the server sending it, your device's IP address, and a sequence number so your device knows what order to put everything back in. And here's the brilliant part. These packets don't all take the same route to reach you. The internet is designed to be flexible. If one cable is congested or broken, packets can take a different path. It's like if you were driving across the country and you hit traffic on one highway, so you just take a different route. Some packets might go through New York, others through Chicago, but they all eventually arrive at your device. When they get there, your phone or laptop looks at the sequence numbers and reassembles them in the right order. If any packets get lost along the way, which happens sometimes, your device just sends a quick message back saying, "Hey, I'm missing packet number 47. Can you send that again?" And the server sends it. This whole system is governed by protocols, which are basically just agreed upon rules for how data should be packaged, sent, and received. Different applications use different protocols. For video streaming, there's one set of rules. For sending emails, there's another, but they all work together to make sure data gets where it needs to go. The physical reality. Let's zoom out for a second and appreciate the physical reality of what's happening. When that data leaves Google's server, it's converted into pulses of light, literally little flashes traveling through fiber optic cables at nearly the speed of light. These cables run under oceans, through mountains, across deserts. They go through some of the harshest environments on the planet. Every 70 to 100 kilometers or so, there are devices called repeaters that boost the signal to keep it strong over long distances. These cables carry up to 10,000 volts of electricity just to power those repeaters. And when the cables finally reach your neighborhood, the light signals get converted to electrical signals by your router. If you're using an Ethernet cable, those electrical signals travel directly to your laptop. If you're on Wi-Fi, they get converted again into electromagnetic waves that your phone picks up. It's honestly kind of miraculous when you think about it. This entire global infrastructure exists just so you can watch cat videos and argue with strangers on the internet. Who runs all this? So, who actually owns and maintains this massive network? It's complicated. The undersea cables are usually owned by consortiums, groups of tech companies, telecom providers, and sometimes governments who split the cost. Companies like AT&T and China Telecom own hundreds of thousands of kilometers of cable. But increasingly, big tech is getting in the game. Facebook owns nearly 100,000 kilometers of cable. So does Google. Amazon has its own private network connecting its data centers around the world. As for who manages everything else, like making sure IP addresses don't overlap or that domain names work properly, that's handled by an organization called ICANN, which stands for the Internet Corporation for Assigned Names and Numbers. They're based in the US, and they basically keep the whole system running smoothly. Why this matters now, you might be wondering, okay, cool, but why should I care about any of this? Here's why. The internet isn't magic. It's physical infrastructure built and maintained by real people and real companies. Those fiber optic cables can be cut by ship anchors or damaged by earthquakes. DNS servers can go down. Governments can interfere with traffic. When you understand how the internet actually works, you start to see it not as this abstract cloud, but as a real, fragile system that we all depend on. And it's not just about understanding your Netflix connection. Almost every critical system in modern society runs on the internet. Hospitals, banks, power grids, emergency services. The more you know about how it works, the better you can protect yourself and make smart decisions about your digital life. The bottom line. So let's recap the whole journey. You type in a web address. Your browser asks a DNS server for the IP address. It gets the address back and connects to the right server. That server breaks the video into packets, each labeled with addresses and sequence numbers. Those packets get converted to light pulses and travel through a global network of fiber optic cables, under oceans, through cities, maybe even past a curious shark or two. They arrive at your device, get reassembled in the right order, and suddenly you're watching a video. All of this happens in milliseconds. It's the result of decades of engineering, billions of dollars of infrastructure, and the combined work of thousands of people around the world. And it happens every single time you go online. Pretty wild, right? If you found this helpful, do me a favor, share it with someone who's still confused about how the internet works. And if you want to dive deeper into topics like this, hit subscribe. We're just getting started. Now you know, the internet isn't magic. It's just really, really clever engineering. And honestly, that's way cooler.